In this video, we are going to discuss variance and standard deviation. In my previous video on mean deviation, in that video we have seen how to find mean deviation about mean and mean deviation about median of a continuous frequency distribution. There we have considered absolute values of deviations about mean and about median. But the degree of variability is very high. Therefore, mean deviation about mean and mean deviation about median is not a reliable measure of dispersion. The absolute values of deviations can also be obtained by taking squares of all the deviations, and we know that squares of deviations are non-negative. So we will investigate if sum of squares of deviations summation xi minus x bar whole square, where I runs from 1 to n, is a reasonable indicator of the degree of dispersion or scatter. To understand this video properly, I request all of you to please watch my earlier videos on mean deviation part 1 and mean deviation part 2. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. Let us investigate whether the sum of squares of deviations from x bar, that is summation xi minus x bar whole square, where I runs from 1 to n, is a reasonable indicator of the degree of dispersion. We will consider a set of 6 observations, 5, 15, whose mean x bar is 30, and summation xi minus x bar whole square I runs from 1 to n for this data is plus 55 minus 30 whole square, which is this 25 square 625 plus this 15 square 225 plus this 25 square 625, which is 1750. And we consider another set of 31 observations, 15, 16, so on and so forth, 45. Total 31 observations. And the mean of observations, say y bar, is also 30. And as usual, the sum of squares of the deviations of observations for this second set from the mean y bar is summation yi minus y bar whole square I runs from 1 to n will be 5 minus 30 whole square plus 16 minus 30 whole square plus 17 minus 30 whole square plus so on and so forth plus 45 minus 30 whole square, which will be minus 15 square plus minus 14 square plus minus 13 square plus so on and so forth plus minus 1 square plus 1 square plus 2 square plus 3 square plus so on and so forth plus 15 square. Here each of 1 square, then 2 square, then 3 square, so on and so forth, 15 square is coming twice. So this summation will be 2 times sum of squares of first 15 natural numbers. Pardon me for saying this 5, this is 15. 15 minus 30 whole square, which equals 2 multiplied by. Now the formula for sum of squares of first 15 natural numbers is n into n plus 1 to n plus 1 upon 6. This will be 2 multiplied by. Here n is 15, so this will be 15 into 15 plus 1, 16 into 2n, that is 15 2s are 30 plus 1, 31 upon 6. 2 1s are 2 3s are and 3 1s are 3 5s are. Multiplication of 5, 16 and 31 is 2480. value of summation xi minus x bar whole square I runs from 1 to n is 1750, and for the second data consisting of 31 observations 15, 16, 17, etc., 43, 44, 45, summation xi minus x bar whole square I runs from 1 to n is 2480. We have graph for the first set of 6 observations as this one, and the graph drawn for the second set of observations is of this type. We observe that the first set of 6 observations has a lesser dispersion 1750, about the mean 30, than the second set of observations, which is 2480, about the mean 30. Even though the first set of observations are more scattered 5, 15, 25, 35, 45, 55 from the mean 30 than in the second set of observations where they are relatively closer to the mean 30, which is clear from these two diagrams. Thus we can say that the square of deviations from the mean is not a proper measure of dispersion. Let us see what we can do to overcome this difficulty. To overcome this difficulty, let us see what happens if we take mean of the squares of the deviations dividing by n, that is 1 upon n, summation xi minus x bar whole square I runs from 1 to n. In case of first data of 6 observations, n equals 6, this will be 1 upon 6 multiplied by 1750, which is 291.67, and for the second set of observations where n is 31, it will be 1 upon 31 multiplied by 2480, which is 80. We see that the scatter or dispersion in the first case is more than the scatter or dispersion in case of the second set. This can be very well seen in the geometrical representation also. In case of the first set of 6 observations, dispersion is more with respect to mean 30, whereas in case of second set of 31 observations, the scatter or dispersion is less compared to mean 30. Therefore, can we say that 1 upon n summation xi minus x bar whole square I runs from 1 to n leads to a proper measure of dispersion, and this number, which is the mean of the squares of the deviations from mean, is called the variance, and it is denoted by sigma square. So variance is given by sigma square, which is 1 upon n summation xi minus x bar whole square I runs from 1 to n. In the calculation of variance, we observe that the units of individual observation xi and their mean are different from the unit of variance, which involves square of the difference between these quantities. Therefore, in order to express the still proper measure of dispersion about the mean of a set of observations is expressed as a positive square root of the variance sigma square, which is called standard deviation sigma. Therefore, standard deviation sigma is square root of variance, that is square root of 1 upon n summation xi minus x bar whole square I runs from 1 to n. We will try to understand the significance of calculating variance sigma square and standard deviation sigma. Find mean x bar and variance sigma square for the data 6, 7, 10, 12, 13, 4, 8 and 12. First, mean x bar, which is sum of observations upon number of observations 8. This is 72 upon 8, 9. So the mean is 9. Now we will prepare a table for finding variance, that is sigma square. First column xi, second xi minus x bar, and third xi minus x bar whole square. For 6, xi minus x bar is minus 3 and square of minus 3, 9. Like that we will write for the remaining observations. 7 minus 2, 4, 10 minus 1, 1, 12, 3, 9, 13, 4, 16, 4 minus 5, 25, 8 minus 1, 1, and 12, 3, 9. Sum of xi minus x bar whole square will be 74. So variance sigma square equals summation xi minus x bar whole square, which is 74, upon n, which is number of observations 8. That gives 9.25. Here mean is 9. The more correct representation of the dispersion about mean is variance, which is 9.25. Variance for these given set of observations is 9.25. So we have variance sigma square equals 9.25. Now we will see what happens to this variance if each of these observations is multiplied by 2. So the new set of observations will be 6 2s are 12, 7 2s are 14, 20, 24, 26, 8, 16, and 12 2s are 24. First, let us find mean x bar, which is 12 plus 14 plus 20 plus 24 upon 8, which is 144 upon 8, which is 18. Let us prepare a table for finding sigma square. So first xi, 12, 14, 20, etc. Next xi minus x bar will be 12 minus this 18, minus 6, minus 4, minus 2, 6, 8, minus 10, minus 2, 6, and xi minus x bar whole square will be minus 6 square, 36, 16, 4, 36, 64, 100, 4, 36. Summation xi minus x bar whole square is 296. Now variance is sigma square equals 296 upon 8, which is 8 ones are 8 threes are 24, 8 sevens are 56, which is 37. We write this 37 as 2 square multiplied by variance before the observations were multiplied by 2, 9.25. So we observe that if each observation is multiplied by a constant k, the variance of resulting observations sigma square becomes k square times the original variance. In this case, this k square is this 2 square, whereas original variance is this 9.25, which we have written here. We will frame the same problem in different way and say that the variance of 8 observations is 9.25, and here if each observation is multiplied by 2, then we have to find the new variance of the resulting observations. Here we do not know the actual observations, so we will assume them to be x1, x2, x3, so on and so forth, x8, and x bar to be their mean. Now since variance is 9.25 and the number of observations is 8, then we have variance sigma square equals 1 upon n summation xi minus x bar whole square, where I runs from 1 to 8. Using the values 9.25 equals 1 upon 8 summation So that gives summation equals 9.25 multiplied by 8, 74. It is given that each observation is multiplied by 2. So we assume new resulting observation to be yi, which according to this condition will be 2xi. So xi will be half yi. So new mean y bar will be 1 upon n summation yi. I runs from 1 to 8. 1 upon 8 summation yi is according to this 2xi. So y bar is 2 times 1 upon 8 summation xi, which is 2 times x bar, because 1 upon 8 summation xi, I from 1 to 8 is x bar. Or from this we can write x bar equals half y bar. Now we will substitute value of xi, which is half yi, and value of x bar, which is half y bar, in this equation 1. So this equation 1 becomes summation half yi minus half y bar whole square, I runs from 1 to 8 equals 74, which is 1 by 4 summation equals 74. Therefore this part becomes 74 multiplied by 4, 296, which can be written as 2 square multiplied by 74. Therefore we can say that variance of new observations equals square of the number by which each observation was multiplied. In this case it is 2, so here it will be 2 square multiplied by the original variance 74. Mean and variance of 8 observations are 9 and 9.25 respectively. If 6 of the observations are 6, 7, 10, 12, 12, 13, then we have to find remaining 2 observations. We assume the remaining 2 observations to be x and y. So the observations will be 6, 7, 10, 12, 12, 13, x and y, and their mean x bar will be, and which is given to be 9. So sum of these observations 60 plus x plus y will be 8 nines are 72. So x plus y will be 12. We will name this 1. Now we have variance sigma square equals 9.25 given, which equals the formula 1 upon 8 summation. So 9.25 equals 1 upon 8 multiplied by 6 minus 9 whole square minus 3 whole square plus 7 minus 9 minus 2 whole square, writing like that, plus x minus 9 whole square plus y minus 9 whole square. This will be 1 upon 8 into sum of these numbers 48 plus expansion of x minus 9 whole square, x square plus 81 minus 18x plus expansion of y minus 9 whole square, y square plus 81 minus 18y. 9.25 multiplied by 8, 74 equals x square plus y square minus 18 into x plus y plus addition of 48, 81 and 81, 162. So x square plus y square minus 18, in place of x plus y we will substitute 12 plus 162 equals 74, which finally becomes x square plus y square equals 80. We name this 2. Now we will square equation 1, so that gives x plus y whole square equals 12 square, which is 144. It is x square plus y square plus 2xy equals 144. But from equation 2, x square plus y square is 80. So this will be 80 plus 2xy equals 144. That gives 2xy to be 64. We name this 3. Now we subtract equation 3 from equation 2 that gives us x square plus y square minus 2xy equals 80 minus 64, 16. Now this part is expansion of x minus y whole square, which is 16. That gives x minus y equals plus minus 4. We name this equation 4. Now we will solve equation 1 and equation 4 together. So if we add 1 and 4 gives us 2x equals 12 plus 4, 16, or 2x equals 12 minus 4, 8. So when x equals 8, from this equation y will be 12 minus 8, 4, and when from this equation x equals 4, y will be again from this equation 12 minus 4, 8. So finally we get remaining two observations to be 4 and 8. This is our answer. If each of the observation x1, x2, x3, etc., xn is increased by a, where a is a negative or positive number, we have to show that variance remains unchanged. Let x bar be the mean of these observations. Then variance sigma square will be 1 upon n summation xi minus x bar whole square. Now if a is added to each of x1, x2, x3, so on and so forth, xn, then the new observations will be yi equals xi plus a. Let mean of these new observations be y bar. Then y bar will be 1 upon n summation yi, I from 1 to n, which is 1 upon n summation xi plus a. From this, so y bar will be 1 upon n summation xi plus summation a. From this, so y bar will be 1 upon n summation xi plus 1 upon n into n times a, because this summation will be n times a. So y bar is x bar from this cancelling n plus a. Now variance of new observations will be, say, sigma 1 square equals 1 upon n summation yi minus y bar whole square, 1 upon n summation. We have yi equals x1 plus a. From this minus y bar equals x bar plus a. So this will be minus x bar minus a, which is 1 upon n summation a minus a is 0. So xi minus x bar whole square, which is sigma square itself. From this, since sigma 1 square equals sigma square, we can say that the variance of new observation remains unchanged or remains the same as the original observations. Now we will verify this rule. We have already found out the variance of a set of these 8 observations to be 9.25. Now we will check whether the variance after adding a fixed number to each of these observations remains the same. So let us add 2 to each of these observations so that the new observations become 8, 9, 12, 14, 15, 6, 10 and 12, and the new mean will be x bar, which will be this 72 plus 8 2s are 16, that is 72 plus 16, 88 upon 8, 11. Now the new values of xi will be 8, 9, 12, etc. And the second column xi minus x bar will be this 8 minus 11 minus 3, this 9 minus 11 minus 2 minus 1, 3, 4, minus 5, minus 1 and 3. And the third column of xi minus x bar whole square will be square of this minus 3, 9, square of minus 2, 4, etc. 1, 9, 16, 25, 1 and 9. This summation is 74, and the new variance, say sigma 1 square, will be 74 upon 8, which will be 9.25, which is same as the original variance 9.25. So we conclude that when each of the observations is added by a fixed number a, the new variance remains unchanged. Pardon me for writing this 12. This should be 14. If you like this video, please like, share and subscribe this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.